So in the last time, I hopefully introduced the idea of integrability in the classical mechanics to you. So in today's 1 hour lecture, I'm hoping to start by talking about some hopefully illustrative examples to show you how kind of idea of integrability actually at work, and hopefully clarify some of the ideas I was talking about last time. And then I think towards the end, hopefully I will get to move on to talk about basically how integrability can be extended to quantum mechanical system. And I think in tomorrow's lecture, my main focus will be talking about, well, I guess one famous example which exhibit the quantum integrability is something known as the XXX spin chain. And I was told that Yongxuan actually talk about it in his lecture. And hopefully I'll be able to discuss, well, basically I'm hoping to discuss something called the algebraic Besser-Ansatz equation, which allows you to actually solve the energy, or basically the eigenvalue for the XXX spin chain Hamiltonian exactly. And in fact, we not only just gonna obtain the eigenvalue for the energies, but in fact the whole powers of other conserved charges also. So hopefully we'll get to that. And the reason we talk about that is this is one, well, talk about the XXX spin chain is because that's actually probably one of the most important, I guess, integrable model which has been applied in the context of, for example, condensed matter, where you use to study critical phenomena, but also you appear over and over again, for example, in the context of theoretical hydrogen physics over the I guess past 20, 30 years or so. So we'll get to that. Okay, so let me try to begin with some examples to illustrate the classical integrability. So, and the problem we are dealing with is the famous, I guess, the Kepler problem. We're basically trying to solve particle and experience some central potential. Usually you do that in the, you study the motion of a planet. So, and usually we are, so I would consider the interaction experienced by this particle by just some general function Vr. And so, and I will basically go from, well, so usually you will begin with some big mass M and small mass small m, and then you will go to the so-called center of mass frame. And we can easily write down, so we are in 3 dimensions, of course. So the equation of motion for this particle, well, for this system, in fact, in the center of mass frame is simply given by something like this. Minus the Vr dxi. And R is, of course, the Cartesian distance. And the Hamiltonian in this case, it's really right, yes. Okay, so we can write down the Poisson bracket for the position and the momentum are simply given by delta Ij. So the dimension of our phase space, in this case, is simply 6. Well, 2 times 3, because we are in the 3 dimensions. So there are 3 position coordinates, and there are 3 momentum coordinates. So in order to demonstrate integrability, we need 3 commuting and conserved quantities. Okay. So, of course, the first thing you notice in this kind of problem is that, well, it does not depend on the angular coordinates, and therefore you expect, for example, things like angular momentum should be conserved. And that intuition is of course correct, that we know that, for example, J, so I call this something like JK equal to X, JK. Okay, so usually we define the angular momentum, and K, 3, and so on. These are, of course, conserved. However, when we calculate one bracket, it does not vanish, right? I mean, hopefully you have all done this calculation before. Right? I mean, people have tried this one before, right? In classical mechanics course. You know, if you're rotating along x-axis and y-axis, and you do it the other way, that'll give you different results. So they do not commute. So those are now the one we want. Okay. So it's not just any good old conserved quantities that you can write down from your Hamiltonian. That's good enough to show the integrability. But rather, we also need them to commute with each other. So, as it turns out, that the 3 commuting and conserved quantities that are, of course, the Hamiltonian itself, almost by definition, and so that's conserved. But it also commutes with, for example, if we take the, say, one of the 3 components of your angular momentum, and also, if you want the square sum of your angular momentum, then you can show that all the Poisson bracket with the Hamiltonian vanishes, so that implies conservation. Okay, and of course also at the same time, if you compute the commutator between each pair of them, that also vanishes. So that indeed, those 3 are really the 3 kind of conserved quantities. So, and actually, they are going to be the kind of action variables. Which we introduced toward the end of the last lecture. So, let me try to use this as an example to flesh out, basically write down some of the other quantities which I defined kind of rather abstractly in the last lecture. So given we have a spherical symmetry, we can change it to a spherical polar coordinate. Theta. So, like in the last lecture, I defined something called I guess I call it a canonical one form, or basically a quantity like this. In the spherical polar coordinates, now we can express them in those coordinates. Bye. Okay. So the Hamiltonian right here. So the Hamiltonian is given simply by half PR squared plus 1 over R squared, B theta squared plus phi squared and plus whatever potential you are given, and the angular momentum squared. Square J3 simply the P phi. So now what we denoted as MF, or basically the surface in the phase space where the conserved quantities are fixed, are simply given by where H, J squared, and J3, the three commuting conserved quantity, are equal to constants. Okay, so that allows us, so we can now, on this surface, okay, we can now express various momentum we have written down here, or basically using those relations, in terms purely as a function of a coordinate. So they know, so the momentum and position are no longer kind of independent variables in your phase space. On this particular surface, we can actually express them as a function of a coordinate. And what's really nice is that now you can actually, so for example, for PR, it's not really just a function of R, because both H and J are now constants. And similarly, for momentum for theta, given by this guy. And of course, P phi itself is just a constant, J3. So I'm basically trying to do a kind of explicit calculation for what various things I was defining last time. So the details may seem a little bit dry, but hopefully you think once, then you feel less scared about it. Then what I was defining to be the generating function is simply, well, so definition is something like this. We can write this also in terms of the r, theta, and phi coordinates. So I really just, the variables. And the nice thing about it now is that we separate the r, theta, and phi dependence into only associated with the momentum for those coordinates only. So we can actually perform the integral, and it's in fact elementary integral, as long as we are given, for example, what the VR is, then we can actually calculate what the PR, well, basically what this guy, PR, which is now a function of R exclusively, we can do this integral. And the same for other direction. So, okay, usually we have some reference point to begin with. And this guy, even I can do it, that's just a constant. So it's really just the difference. Okay, so this is P phi. Okay. In this case, it's a function of phi only, but it's only really just a constant. Okay. So that's our generating function. So, and for the generating function, we can calculate, for example, all the action variables associated with the angle variable associated with the three action variables. They are given by the partial derivative of the generative function with respect to the action variables. So So those will be the action. So the angle variable. Okay. And the evolution of those angle variables are simply given by H dot. It's given by computing a commutator. So, sorry, it's simply given by EH. H 1 and also those two should not be surprise to you because the Hamiltonian do not have a explicit dependence on the angular coordinates. So that basically says that all the action, so all the angle variables for J squared and J3 are really just constants. And while for the time, this one we can actually solve for. So this basically tells you the square J3 was constant. Okay. And while for the first equation, what we have is that right here, that we can actually solve for what the angle variable actually is. And we get a relation between the radial coordinates and the time coordinates. So that's pretty much most of the planetary motion for you. Depends on what kind of potential you have. Okay. As long as it only depends on the radial coordinates. You can calculate, for example, your period of your, how your satellite going to go around your heavy stellar objects and all that. Another little comment is that this condition that the psi J squared equal to 0, when you write out what the angle variable actually is, then this condition, so the condition equal to 0 actually implies that the phi dot equal to J3 over sine squared theta, J squared minus J3 squared, J3 squared sine squared theta phi dot. But this is precisely the condition needed to ensure J1 and J2 are constants. Okay, so indeed, from those angle variable, we can still see the expected conserved quantity J1, J2, and of course J3, which is one of the action variables. Okay, so that was basically how to calculate various kind of quantities that I defined from the last lecture in a classical mechanics problem. I mean, I gave hopefully a sufficiently general example would you encounter this kind of example, but different kind of VR. Hopefully encounter quite a lot in your career so far. Okay. Any question? I hope this is almost too boring to be this hour. But anyway, so. Okay. So let me try to. So another important notion which I introduced from the last lecture was the lax pair. So in the next example, I would like to talk about how to compute, or basically what a lax pair actually looks like, if you want. For actually a whole series of interesting Hamiltonian, which some of you may encounter For example, if you are doing condensed matter or doing high energy physics, those Hamiltonian you probably have seen it before, but you may not have seen them in your conventional classical mechanics courses. So finite. For 1D many body problem. Okay. So basically we are dealing with, again, the Hamiltonian looking something like this. So there are some coefficients which usually go by the trade name coupling constant. Then you just have some generic pairwise interactions. So by the way, the reference is actually from a kind of excellent set of review lecture, I think actually almost more than 30 years ago, by Olshansky. And Carol. So those are actually very good. Actually, they wrote two sets of review. One set on the classical integrability. And another actually just on how to quantize those various kind of classical mechanical systems that which exhibit the classical integrability. So we now one will be quantum integrability. Okay, so we are looking at 5 different kinds of. So in some sense, I'm giving kind of 5 different examples that which we may not have seen before in classical mechanics. Those systems actually exhibit kind of classical integrability, and they are specified by different potentials. So I will call them, for example, the first one is will be y is actually equal to 1 over y squared. Okay, and the second one is equal to, so Vy equal to a squared, so a just some constant, which we can dial, sine square ay, and the third one goes like a squared over sine square ay, and then the fourth one, which goes like a squared p ay w1 w2, and this guy is the famous Weierstrass function, which is given by p z omega 1 omega 2 is equal to 1 over z squared plus m squared plus not equal to 0. If one day you are doing